So this video is going to be dealing with factoring and solving polynomials, okay, is what this is going to be talking about. Okay, we've been doing this, but I just want to emphasize a few things. So if I am talking about using synthetic division to factor and to solve these polynomials, there's a couple of theorems that you want to know, okay? And one of those theorems is called the remainder theorem. Is the remainder theorem. And what this theorem states is the following. If P of X, okay, our polynomial, is a polynomial and A, okay, A, the letter A, variable A is a number, and P of X is divided by the factor, I'm putting in parentheses, X minus A, then the remainder is the same as substituting in to the polynomial A, where A would make this factor X minus A 0. So an example of this, let's say we're going to do the following problem, okay? So let's say that we have P of X is equal to X to the third plus 8x squared minus 5x minus 84. And let's say that what they wanted us to do is they want us to evaluate when X is equal to -5. So one way to do that, the old-fashioned way, is to put -5 into this equation and go -5 to the third plus 8 times -5 squared minus 5 times -5 minus 84. And let's say I was doing this without a calculator. This would be a little bit of effort. So -5 cubed is going to be a -125 plus 8 times, this is going to be a 25. A -5 times a -5 is a positive 25 minus 84. So I'd have a -125. 4 times 25 would be 100. So 8 times 25 would be 200 plus 25 minus 84. Let's say that I take and I add these two together, and I get 225. Okay, so I'm adding these two together. Then I have minus 84. So that would be a positive 100 minus 84, which would be 16. So P of -5 is equal to 16. Now, instead of substituting in -5 into this whole entire polynomial for each of these x's and cubing and squaring and multiplying and combining like terms, what we could do instead is take the same -5, okay, the same -5, put it in the little box and do synthetic division. So I'm going to take my coefficients, which were 1, 8, -5, -84, making sure that I have my terms in descending order and I'm not missing any term. If I was, I would put a 0 in its spot. Okay, bring down my 1. 1 times -5 is -5. I add, I get 3. 3 times -5 is -15. I add, I get -20. -20 times -5 is a 100. I add, I get a 16. Now, this is my remainder, okay? This right here is considered our remainder. And what I really did was I really was dividing by an x plus 5. That's really what I was dividing by. And I really got back an x squared plus 3x minus 20 plus 16 over x plus 5. That's really what I was doing. That's really what I got back, which means x plus 5 was not a factor. But this remainder is the same as when I substitute that in. That's what that theorem's saying. That whatever number I put here in my synthetic division, whatever I get out for my remainder is basically the same as me putting in a -5 into the polynomial and seeing what I get out. So you can also think of this as an actual point on the polynomial graph. This is really the point -5, comma 16. So if I go to my graph of this and I put in a -5, I am going to get a 16. So that's what the synthetic division is doing. This remainder is my remainder when I'm dividing. And if I did have a -5 here, really I was dividing by an x plus 5. But this -5 is also the same as substituting into the polynomial. And what I get for my remainder is the same as me substituting in -5. Okay, so next situation. So the next theorem I want to talk about is called the factor theorem. And the factor theorem states the following. If P of X is a polynomial, then I'm just going to put this in parentheses. X minus A is a factor of P of X if and only if and only if, and I'm just going to put in here just kind of a side note. If and only if, the shorthand is IFF. Okay, that's if and only if. But in this situation, if and only if P of A is equal to 0. So we saw in this situation here that when I do synthetic division, my remainder is really the same as if I had substituted this number that I'm using for my synthetic division, which is what makes this factor 0, okay? It's the same as substituting it in. And so if it's going to be a factor, want it to go in evenly and make it be an actual 0. Okay, I want this 0 to actually make the polynomial 0. And in this case, this wasn't. I got a 16. So, for example, let's say that they gave us this situation. And they said, okay, we want to know is x minus 3 a factor of the polynomial p of x equals x to the third plus 5x squared minus 17x minus 21. So I want to look at this factor and go, okay, what is going to make that 0? Negative, sorry, not negative 3, positive 3 is going to make that 0. So I'm going to do synthetic division with a positive 3. Again, write my factors, my coefficients in descending order, 1, 5, negative 17, and a negative 21. Bring down my first number, which is a 1. 1 times 3 is 3. I add, I get an 8. 8 times 3 is 24. And I add, I get a 7. 7 times 3 is 21. And I add, I get a 0. So since my remainder was a 0, remainder equals 0, x minus 3 is a factor. Okay. It also tells me that because of that, okay, because of that, also x equal 3, since 3 makes x minus 3 0, is a solution. Okay, that also tells me that. Now, if they ask me to factor completely, at this point, I know that I have x minus 3 times this depressed polynomial, x squared plus 8x plus 7. And I could now look at this polynomial, which happens to be a quadratic, and factor that. So I still have my x minus 3. What multiplies to 7 and adds to 8? An x plus 1 and an x plus 7. So this right here is the factors of x cubed plus 5x squared minus 17x minus 21. So the next thing I want to talk about is the theorem that allows us to do the P over Q's to find our possible rational solution. So this is called the rational zeros theorem. Rational zeros theorem. And it states the following. If a polynomial function has integral coefficients, which means integers for the coefficients, not fractions or decimals, okay, or imaginary. So if a polynomial function has integral coefficients, and if it has a rational 0, and I'm going to just get my fraction thing here, P over Q, where P and Q are relatively prime, then P and Q, okay, then P is the factors of the constant term, and Q is the factors of the leading coefficient. Okay, so let's say we had the following problem. And I'm going to break it up into kind of 2 questions. Okay, so let's say that they only asked this, and they said that they wanted us to list all possible rational solutions of the following. And let's say it is P of X is equal to 12x to the third minus 8x squared minus 3x plus 2. Let me just make this 2 a little nicer. So what we're going to do is I'm going to look at this for my P, and I'm going to look for, sorry, my Q, and this for my P. So again, this is going to be my Q, and all the factors of 12 are positive and negative. 1, all of them are plus and minus. I'm just going to write positive, negative 1, 2, 3, 4, and 6, and 12. Forgot my 12. And all of my ones for my P are going to be positive and negative 1 and 2. So when I am trying to find my possible rational solutions, list them, then this is possible, not necessarily that these are the solutions. If this is a degree 3, only 3 solutions will there be for a polynomial of degree 3. So I'm going to take all of my P's, which are going to be a positive, negative 1 and a positive, negative 2. And I'm going to put it over all of my Q's, which is a positive, negative 1, 2, 3, 4, 6, and 12. Okay. So then when I list them out, I'm going to take all the different combinations. I'm going to put my 1 and 2 over each of these different denominators. Okay. So first I'm going to put them over 1, and that's going to give me a positive, negative 1 and a positive, negative 2. When I put them over 2, I'm going to get a positive, negative 1/2, and 2 over 2 is a 1. I already have that. I don't need to list it again. Then I'm going to put them over the 3. So I'm going to get a positive, negative 1/3 and a positive, negative 2/3. Now I'm going to put them over 4. So I'm going to get a positive, negative 1/4. And then when I do 2 over 4, 2 over 4 is a 1/2. I already have it. Now I'm going to do 6. So now I'm going to have a plus or minus 1 over 6. And when I do 2 over 6, 2 over 6 is a 1/3. So I already have that. And then I'm going to do plus or minus over the 12. So plus or minus 1/12. And then when I do 2 12ths, 2 12ths is a 1/6. I already have it. So I have 1, 2, 3, 4, 5, 6, 7, 8, 16 possible rational solutions. These are my possible rational solutions right here. All of those. Okay. So now, if they say, find the solutions to 0 equal, let's say 12x cubed minus 8x squared minus 3x plus 2. So I'm dealing with the same problem here, but now I'm actually going to solve it. I'm going to use synthetic division, and I'm going to use only these numbers. Okay. So I'm going to do it in a table form. I may or may not get it first try. So I have a 12. I have a negative 8. I have a negative 3, and I have a 2. What I always do is I always look to see what I have here, because that would really be my 0. So at 0 on my graph, I'm at 2. Okay, I'm really at 0,2 on my graph. So I'm 2 above my x-axis. I like to kind of think about where I am in the graph. I want to be on the x-axis. I want a 0. So let's say I try my 1. I bring down 12. 12 times 1 is 12. I add it, I get a 4. 4 times 1 is 4. I add it to my -3. I get a 1. 1 times 1 is 1. I add it to 2. I get a 3. So you see I'm going up. Okay, I'm going up. Now, I also notice, and I'm going to talk about this with you guys, that when I use a positive number and I ended up getting all non-negatives here, okay, this situation right here is going to give me what we call an upper bound. And that upper bound happens when I have a positive number that I'm trying and I get all positive numbers back. So this occurs if get all positives back when you do synthetic division. When you do synthetic division with a positive number. Okay, that's what happens. So at this point, I am not going to try anything greater than a +1. I'm not going to try 2. It's not going to work. So I'm going to go the other direction. Okay, and I am going to do a, sorry, just trying to get my black here, do a -1 this time. So I still bring down my first number, 12. -1 times 12 is a -12. I add it to -8. I get a -20. A -20 times a -1 is a +20. I add it to -3. I get a 17. A 17 times a -1 is a -17. I add it to 2 and I get a -15. Now, what you want to pay attention to is the following. I ended up in this situation. Let me get a different color. I ended up in this situation with I want to do that, with a negative number that I'm trying, and I ended up with alternating signs. That is going to tell me that this is going to be a lower bound. Okay, so this is going to be a lower bound. And that occurs if you get all, not all, alternating is what I'm trying to say. Alternating signs when you divide, well, I should say you do synthetic division with a negative number. So this is going to be a lower bound. So what that means is I'm not going to try that -2. It's not going to work. And the reason this is happening is because these graphs, this is a degree 3 polynomial. So a degree 3 positive polynomial looks something kind of like this, just kind of a rough sketch. So this upper bound here, I'm on the rise. It's going to keep going up. Any number I try after once is going to keep getting bigger and bigger and bigger. Right here, this -1, I'm on the way down. Every number I try in front of -1, -2, -3, and so on, it's going to just keep getting down, going down, down, down. It's not going to be turning and coming back up. Okay, so it's a waste of your time to try anything after the 1 or in front of the -1. So something else I want you to notice is that in between this 0, which gave me 2, and this -1, which gave me a -15, you will have a 0 in between, because at 0, 2, which is this, I'm above the x-axis. This one right here is really a -1, -15. So that's below the x-axis. So if I'm above and then below, somewhere in between my 0 and my -1, I had to cross. So I'm going to try one of these numbers between. Okay, we call that the locator theorem. I'll write it here in a second, but let's just try one of these numbers. So let's say I try a -1/2, and let's see what happens. I bring down my 12. 12 times a -1/2 is 6. I add it, I get a -2. -2 times a -1/2 is a 1. I add it, I get a -2. Hold on a second. Hold on. I brought down my 12. I got a -6. Oh, sorry. I got a -6. I apologize. Start again. Okay. So 12 times -1/2 is a -12. I'm sorry, a -6. When I take a -6 and add it to a -8, I get a -14. I apologize. -14 times a -1/2 is a +7. When I add that to a -3, I get a 4. 4 times a -1/2 is a -2. When I add it to 2, I get a 0. So I just found a 0. Okay, I just found a 0. But let me just again talk about the situation that I just was describing. Where here, which was really 0, 2, and here, which was really -1, -15. Let me smooth that over. -1, -15. By the location theorem, what has to be true is the following. So if you are above the x-axis at A, or I'll just say this, at x equal A, and below the x-axis at, let's say, x equal B, what has to have happened is there is a 0 in between x equal A and x equal B. The polynomial must cross the x-axis between x equal A and x equal B. So that's why when I am always looking at my 0, which would have given me a +2, I'm above the x-axis. Here at 1, I was above the x-axis. So there's no 0 in between here. And we saw that this is going to keep getting bigger and bigger. So here, between this -1 and this 0, I was above, I am below. I have to cross somewhere in between my 0, 2 and my -1, -15. So I tried an x value in between these. I tried -1/2 and I ended up getting my 0. Okay. So now I am going to take this situation here, and I know that x equals -1/2 is a solution. And so now I'm going to take that depressed polynomial, 12x squared minus 14x plus 4 = 0, and solve. Now, when I'm doing that, I happen to notice that I can divide everything at least by 2. So 6x squared minus 7x plus 2 = 0. And then I'm going to factor, okay? So let me just tell us what the factors are for this. So when I factor this, I'm going to end up getting a 3x minus 2 and a 2x plus 1. So that means that I'm going to get here a 2/3, and I get here a -1/2. So this one should have been, I apologize, positive 1. Sorry, a -1/2. I apologize. That's a -1/2. So this is going to be a positive 1/2. So my solutions are going to be, again, x equal -1/2, x equal 2/3, and x equal 1/2. Those are my 3 solutions. Now, I am going to say this. Up here, I was saying that right here, we're not seeing a 0 between 0, 2 and 1, 3. We're not seeing it because I did not have it be above and below. But that doesn't mean that there's not a 0 in between there. We see that 2/3 actually gave me a 0, and that is in between 0 and 1, and 1/2 did. But there's no nice integer 1 that's going to be between these. Okay. So my 3 answers, again, x equal -1/2, x equal 2/3, x equal 1/2. And in this problem, we talked about a few things. We talked about the rational zeros, finding our rational zeros. And when they ask you just to find your possible rational zeros, they mean list them. We're not actually solving. I took that problem a step further and I actually solved using those. And we saw an upper bound situation where when I try a positive number, I get all positives back. That situation is an upper bound. If it's not the highest bound, it just means don't try anything above that. You've reached a spot where it's not going to come back down and cross the x-axis again. Here, when I tried a -1 and I got alternating signs, again, this is when I try a negative. If I get alternating signs, that's a lower bound. Okay, this graph's not going to come back up. It's going to keep going down. Location theorem is where if I notice that I try one number and I'm above, and I try another number and I'm below, somewhere in between those two x's that I tried, it will cross the x-axis. So we tried a number in between our 0 and a -1, which I had a lot of them I could choose from, but I just tried a -1/2 and it worked. The next thing I'm just going to point out to us, and I kind of talk about this when it happens in the problems, but we have something called a corollary of the rational zeros theorem, which states the following: if the leading coefficient of a polynomial function with integral coefficients, so again, we're dealing with only integral coefficients, not fractions or radicals or imaginary, and that lead coefficient is a 1, okay, which basically means our Q is going to equal a 1, then any rational zeros are going to be integers. So in that last problem that we were working out, up here, my lead was a 12. So my denominator, I had all factors of 12. So I had a lot of fractions. But if my lead is a 1, I'm actually going to only have integers to try. So let's say, for example, we have the following. And they say, list all possible rational solutions, okay? Of P of X is equal to X to the third plus 3X squared minus 25X minus 75. So in this situation, our P up here was a 12 and our Q, I'm sorry, our P was a 2 and our Q, the number in front, was a 12. Down here, this is going to be a simpler problem because my Q is going to be a 1. My P is going to be a 75, so I'm going to have more choices for that. Okay, so my P being a 75, I'm going to have as my choices plus or minus 1, plus or minus 3. 3 goes into 75, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. That's a lot of choices. But the nice thing is that my Q is only going to be our plus or minus 1. So when I do my P over Q, I'm putting all of these over 1. So I really just get my P, my plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, plus or minus 75. I get no fractions. And then I would try those.